think we're all set and ready to stream. Let me switch over to my main screen and figure out where we left off yesterday. Here we go. So what did we do? We're in the middle of trying to get this function thing to work, and we were failing miserably. So let's see if we can revisit that. Get status. Get. No. We're going to just take a look at the locks function. And what we were trying to do, it was... Right, that's it. We were trying to make this an RC, and that didn't work. And we did put this back, right? In build. Yeah, we did put it back. Okay, so that means in our interpreter, we were doing this and we don't want to do this anymore. We're just going to pass this in as a reference to the function statement. And then we'll figure things out from there. So if we give this a function statement, every time we visit a function statement. Hey Nick Flex, how are you? Every time we have this, we're going to create a new environment and a new function object. So if we're going to do that, what we can do, okay, how about this? How about this as an idea? We can, we can just generate inside the locks function, right? We can generate this name, token, params, vec token. You know, actually, what we can do, we can go one step further and make this all reference counted. So we're not copying the entire vec. We can just copy the reference, just like, you know. So it's kind of simulating the way Java works, maybe. Let's see if we can do that statement like that, and then these will be converted over. Which means we have to change them here. RC and like that. And then we can do is just generate like this. Name is going to be declaration.name.dupe because we have the dupe function on the token. Params is just going to be RC clone of declaration.params, and then the body is going to be same thing. Will that work? And then down here, we don't have declaration anymore. We just have params directly. Same here, right? And here, and here. I want to fix this into business also. Token not found in the scope. Okay, that's easy to fix. Use create token star. Oh, RC doesn't exist. Okay, so we have to add that here. Expected reference found. Oh, okay, we can just borrow those guys. Okay. And what are the other errors? Expected RC. Okay, we don't want to do that anymore. Okay, will I clean that up? Oh, we still have two errors. Oh, right, when we generate it inside the parser, we have to also generate it with an RC. So we have to say params is equal to RC new params. Right? Oh, and the body too. Duh. RC new, we can just put that up here. Okay, we have two warnings. Deref is not used inside locks function. Locks function. Get rid of deref. And We're good. Okay. Oh, Zeta numbers. Hi. How are you? Okay, so let's see. Well, does that clean everything up? Because now it compiles. Can we actually write a function? Fun foo. I don't know. Print bar. Didn't complain. Oh, look at that! It works. We can now call functions. And we should be able to pass in parameters, right? Like a. Print a times 3. So bar of 12 is 36. Neat. Oh, I hit return without entering anything, and that apparently means stop. Okay. Fun bar. Well, let's create a foo that uses a global variable, right? So we'll have a local and print global times local, like that. And we'll set a, if I try to run it, it should complain about global doesn't exist, undefined variable. I can create now a global variable and call foo of 27. What's 27 times 12? Yeah, 324. Okay, so that's all working with the scopes and everything. So, oh, I should be able to set a local too. Bar local equals 3. And then pass in, and foo of 9 should still be 108, right? Yes, okay, so that local overshadowed, or shadowed the global local, so to speak. Okay, nice. So we got that working. And all we had to do is destructure everything. Git diff. What did we do? We added this function. We're no longer doing this to-do business now. And now, yeah, so we just pull out all the data and clone everything. Okay. And that seems to do the trick. Whew. I couldn't come up with this last night, or yesterday rather. That's too bad, because that was pretty easy. Okay, so git add generate and source, git commit, section 10.4 functions can now be called. Okay, so now we get to do return statements. All right. Let's dive in. Hotel California of data. We can get data into functions by passing parameters, but we've got no way to get the results back out. If locks were an expression-oriented language like Ruby or Scheme, the body would be an expression whose value is implicitly the function's result. Yeah, so it's similar to Rust, right? Where the last statement of a Rust function is the return value. But in locks, the body of a function is a list of statements which don't produce values. So we need dedicated syntax for emitting a result. In other words, return statements. All right, so the return statement is just return followed by 0 or 1 expressions followed by a semicolon. We've got one more, the final in fact, production under the venerable statement rule. Okay, so this is the last statement. Production. Nice. A return statement is the return keyword followed by an optional expression and terminated with a semicolon. The return value is optional to support exiting early from a function that doesn't return a useful value. In statically typed languages, void functions don't return a value and non-void ones do. Since locks is dynamically typed, there are no true void functions. The compiler has no way of preventing you from taking the result of value of a call to a function that doesn't contain a return statement. What is this going to do? Let's find out. Cargo on. Oh, right, we don't have return statements yet. Okay, so we can't even try it. This means every locks function must return something, even if it contains no return statements at all. We use nil for this, which is why locks function's implementation of call returns null at the end. In the same vein, if you omit a value in a return statement, we simply treat it as the equivalent to return nil. Okay, that's fair enough. And then we're going to add the return statement. After print, we'll put return, and it takes a token keyword and an expr value, just like that. It keeps the return keyword token so that we can use its location for error reporting. Yeah, it's the same way we use paren for other things. We parse it like other statements, first by recognizing the initial keyword. Okay, so in our parser statement, we have this return statement between print and var. Oh no, sorry, between print and while. I was looking at the wrong thing. Okay, right here. If self is match. Okay, and that branches out to the return statement, and we're going to put this after print statement. Okay. I don't think it matters where it goes, but we'll just try to be consistent. There we go. And it's going to return a statement. Let keyword is previous, self previous, and then let value is going to be either null or an expression. So we're going to do this if self check token type semicolon. I'm just flipping these around because there's no reason to have a not check in there. It's easier to read when there is a check. If it's a semicolon, then there's no value. Otherwise, it's some expression, self expression, like that. We're going to do self consume token type semicolon, expect after return value, and then we're going to say okay on statement return statement, and I don't know what it looks like. I don't remember what it looks like. Okay, it has a keyword and a value. Oh, this needs to be an option, right? Like that. Otherwise it won't, we can't do it a sum none thing. Okay. So we have a keyword. And a value. I think it can all go right there, right? Oh, right. Let me stub this out. So that we can get this to compile, and then keyword doesn't work. Why not? Expected struct token. Oh, right, I have to dupe it. There we go. Okay, nice. And the warnings are just because we're not using that. Oh. This warning here, we got to take care of that one. Okay, done. So after snagging the previously consumed return keyword, we look for the value. This is where we snag it. We look for a value expression. Since many different tokens can potentially start an expression, it's hard to tell if a return value is present. Instead, we check if it's absent. Since a semicolon can't begin an expression, if the next token is that, we know there must not be a value. Right. All right, so now returning from calls. Interpreting a return statement is tricky. You can return from anywhere within the body of a function, even deeply nested inside other statements. When the return is executed, the interpreter needs to jump all the way out of whatever context it's currently in and cause the function call to complete, like some kind of jacked up control flow construct. For example, let's say we're running this program and we're about to execute the return statement. The Java call stack currently looks roughly like this. So visit call expression, do the call on the locks function, execute the block, visit the while statement, visit the block statement, execute the block, visit the if statement, visit the return statement. There's I think there's a then in there as well, but that's okay. I don't think there's a visit then statement. I think it's just execute block for that, and then return statement. We need to get up from the top of the stack all the way back to the call. So all of these need to disappear. I don't know about you, but to me it sounds like exceptions. When we execute a return statement, we'll use an exception to unwind the interpreter past the visit methods of all the containing statements back to the code that began executing the body. Oh, that's very similar to the way we did break statements. Oops. I forgot to save that. Oh, yeah. So how did we do visit break statement? Oh, that was in interpreter. Yeah. So all we did was return. Sorry, we returned a break using the error result, and then the while statement caught the break and did its own break out of the while loop. So I think that's the way we're going to handle with returns, right? All right, so the visit method for our new AST node looks like this. Oh, right, when we execute a return statement, we'll use an exception. Well, in our case, we're going to use an error to unwind the interpreter past the visit methods. So in visit return statement, which is right here, object value is null. If statement value is not null, then value is evaluate. Otherwise, and then throw. Okay. So in Rust, we're going to say if let some statement value. No, let some value is equal to statement value. Then we're going to error. Oh, right. We need to create a return type. So we have break. Let's create a return value, which contains a value, which is an object, right? Because we're returning an object. We're returning value. Value is an object. So this has to be an object here. And then I think we have a match somewhere down here. Yeah, that we have to ignore. Okay. Blocks results return value. Like that. Yeah, I didn't finish this thing yet. But I think this does the trick. No, it doesn't do the trick. Oh, object not found. Okay, use create object. Like that. Okay. So back in the interpreter, let's do this again. If let some value is equal to statement value, then we're going to return error of locks error. We'll make a constructor for it, and then self-evaluate value. Oh, yeah, self-evaluate value, right? Else oops, I got the wrong brace here. There we go. Otherwise it's going to be error locks error return value object nil. We're going to return a null. Right, and now we have to write the return value function. Oh, locks error is not. Oh, locks result. R-E-S-U-L-T. Wow. Result. Now we have to write this. Okay. Easy enough. Let's put it up here, I guess. Pub fun return value, and it's going to take what, an object or value, which is an object. I'm going to return a locks result, and we'll do locks result of return value. Value. Is that it? Nope. expected enum object got found enum result. Oh, right. I need to question mark that. Ooh. Right, and this is the return value runtime exception that we just did. If we have a return value, we evaluate it, otherwise we use nil. Then we take that value and wrap it in a custom exception class and throw it. So that's that. We did that on the other side. This class wraps the return value with the accoutrement Java requires for runtime exception class. Okay. Weird superconstructor call with those null and false arguments disable some JVM machinery that we don't need. I guess that's that. We don't have to worry about that in Rust. Since we're using our exception class for control flow and not error handling, we don't need overhead like stack traces. Oh, okay. That's probably what that is all about. For the record, I'm not generally a fan of using exceptions for control flow, but inside a heavily recursive tree walk interpreter, it's the way to go. Since our own syntax tree evaluation is so heavily tied to the Java call stack, we're pressed to do some heavyweight call stack manipulation occasionally, and exceptions are a handy tool for that. So I don't think Rust has the same kind of overhead that JVM does for exceptions, because it's just like another return type. Right? We're just returning a value, whether it's via an error or via OK. I think it's the same cost. We want to unwind all the way to where the function call began, the call method in locks function. Oh, okay, yeah. So in locks function, where do we did the call here, interpreter execute block. So this thing is going to return, what's the way to do this? Because there can be three different things, right? If I do a match, that might do the trick. Great, because it can be a locks result of a return value of some v. It could be a locks result of anything else. It could be an OK. Right, we have to handle that case because this returns a result, and I don't think that ever gets used. Panic. OK result from function call. So I don't think that will ever happen, and then everything else gets tossed up. Oh, so any other error. Oh, that's right. So this must be an error. E. And we'll just toss it back E. Right? And then the return value is going to be, we're just returning the return value, which is this thing here. So this is going to be OKV. Can we do that? That's error E. Can I do this even? There's a comma there. I can't use the question mark because we want to trap this one case and make it an OK. I guess we could also just make this nil here, but I don't think we ever should get this, but we'll find out. Let's find out. Epic Blog says, using exceptions for control flow. Here's his justification. Here's his justification. I don't know. So we'll see if the C version obviously is not going to have exceptions. Right, because I think the C locks is just pure C. It's not C++. So there's no exceptions going on there. So we'll see how they do return statements. I once saw a tokenizer written in C++, which threw tokens, and handlers caught the exceptions. Maybe not a literal nightmare, but not far from it. Okay. I mean, that sounds like one of those, I have a hammer. Everything looks like a nail. Ooh, so I can't do this. Oh, return value like this. Sorry, I messed up. So this has to be, come on, value like that to destructure it. And there we go. Yeah, okay. We wrap the call to execute block in a try catch block. When it catches a return exception, it pulls out the value and makes that the return value from the call. If it never catches one of those exceptions, it means the function reached the end of the body without hitting a return statement. In that case, it implicitly returns nil. Oh, right. So if we never hit a return statement, that isn't a case where we'll hit OK here. Okay, let me just prove that. Cargo run. Okay, compiles. Fun foo. If I just say print bar and don't have a return statement, is that going to be the thing that panics? Yeah. Okay, so we're going to have to generate. We're going to have to generate the return value from here. So this just becomes OK object nil. Right, and then let's try that. Copy paste this guy. Foo like this. And runs bar and it doesn't return anything. If I say print foo like this, it should say nil. Yes, good. Good. Aristotle, good. Thank you for the follow. All right, so we have return statements working. Oh, let's try this little function here. Make sure we have everything working because this is recursive now, right? We're doing the Fibonacci. You might notice this is pretty slow. Obviously, recursion isn't the most efficient way to calculate Fibonacci numbers, but as a good micro benchmark, it does a good job of stress testing how fast our interpreter implements function calls. As you can see, the answer is not very fast. That's okay. Our C interpreter will be faster. Okay, so let's see how slow this is. Recursive fib.logs. Right, so we have a recursive fib. We're going to print out 0 to 19 and see how slow it is. Cargo run recursive fib. Oh, I mean, that's not exceptionally slow. And this is debug mode. Cargo build release. Time. Target release locks AST. Recursive fib. Boom. I don't know. 30 milliseconds. That's not too bad. Maybe Java is a little slower. Let's see what the debug version, how slow the debug version is. All right, so that's 310. That's 10 times slower. Yeah, and if we were running the Java version, right, the Java version is going to be an interpreter running an interpreter. So yeah, it would be a lot slower, is my guess. I mean, we're compiling this thing down to native machine code. So, all right, so we have this git status, git add. Let's do a diff here. Just I want to see what we did. So we did a return statement here. We added a new return type for the locks result. And so how we visit the return statement is we throw the error if we need to. And this is how we handle return codes. And then the parser has to handle the return statement. And this is how we build the return statement tree node. Okay, good. Git add generate and source. Git commit. Section 10.5. Return statements. Nice. What we haven't done in a while though is clippy. Let's see if clippy has any complaints. Clippy has some complaints. Comparing trait object pointers compares non-unique vtable address. I don't know what that means. And I don't know if that means that this is an invalid way to do pointer equality for our callables. This I can fix. This is pretty straightforward, right? All it's saying is do this. But this thing. Is there a different way that we can compare equality for the function? I mean, they're both din callables, and we just want to see. I just want to see if they refer to the same function. For more information, visit this thing. Okay, let's visit that thing. Comparing trait object pointers compares an and vtable address. I guess we can just remove the and. Compares vtable addresses, which are not guaranteed to be unique and could vary between different code generation units. Furthermore, vtables for different types could have the same address after being merged together. I still don't understand. I understand all the words individually. I don't understand the meaning behind the words. Probably because I don't know. So this is probably talking about the way Rust implements vtables. The fact that vtables for different types could be merged together is not something I can picture in my head. So you know what I'm going to do? I'm going to do the best thing I possibly can do, is just ignore it. So this is on by default. We could allow it. Consider extracting and comparing data pointers only. But that's the only data pointer I have in callable. This is one thing. I'm going to allow it for now, and then if something breaks later, we can just blame that and say, oh, that's what it is. Zeta number says there's standard pointer equals. You could use that on immutable borrows. Okay, let's take a look at that. This is the same as using an equals operator, but less generic. The arguments have to be const star. The star const t raw pointers, not anything that implements partial equal. This can be used to compare ref t references by their address rather than comparing the values they point to, which is what the partial equal for %t does. All right. I can try it. Let's try it. Use standard pointer. I'll use standard pointer, that way I can say pointer : equal like that. I think that might be, oops, more readable. Pointer equal self another. I don't know if I have to put the ampersands there because they're already ampersanded. But these have to be the pointers. They have to be the refs. Epic says, that whole, I understand all the words, but I don't understand what the paragraph's trying to tell me. Happens to me a lot when reading the Rustonomicon. Yeah, so I think it's just a matter of keep on hacking at it until eventually you grok it, right? So this didn't complain. And I don't know how to test this. Maybe we should make a little test module to see and create two callables and see if they're equal to each other. Maybe that would be the best approach, and then we can compare and see if these. Because I haven't done a test in a while. Test mod tests. Use superstar. How hard is it going to be to create one of these things, though? Fn compare equality. Zeta number says you probably should dereference func field. I think so. Like this. Well, that also checks. So. But what we can do is we can create two din callables. Or two locks callables. And callable already has locks callable, so we can just create a callable, maybe? Oh, no. We have to create something. Is there another way to do this? I just want to create a callable. And doing locks function is going to be complicated. Oh wait, how did we do the native one? Right? We just implemented native clock like this. We implemented locks callable for native clock. So maybe we can do that inside here. Struct foo impl locks callable for foo and fn call. Just copy this and paste this. We don't care about anything. I'll just say okay. Object nil. And the arity will be 0. And then, oh, okay. So dereference the func and then get the reference to it like this is what Zeta Numbers is saying in chat. Okay, let's try that. And then we have a toString self, which returns a string, which is just going to be a string, because I don't care. And then I should be able to grab 2 of these guys, create 2 of them, right? Let foo1 equals foo. Let foo2 equals foo, and they should be not equal. Let callable 1 is equal to callable. I hope it works too, Zeta Numbers. I hope so, but that's why I'm writing the test, right? So how do I create a callable? I don't even have something that creates. I can just create it directly. So just func foo1 and foo2, right? And these should be not equal. Assert, right? Not C1 equals C2. C1 not equals C2. Duh. I haven't run the tests in a while, so I may have broken them along the way. Of course I did. What did I do? Oh my god. Okay, so we have a problem here. RC new. Yeah, because these are 2 different RCs, we're going to have 2 different functions, or 2 different, yeah. So these are going to be not equal. But it looks like I broke all the tests in environment when I modified the way we do environments. I can't run my tests now. Okay, but I can run just this one test. Nope, it won't let me do that just one test. I have to get it to compile first. All right. What I'm going to do then is ignore the problem. I'm going to leave it like this, all right? Because we'll see if these pointers are equal, right? We're going to deref the func and then take the reference to it and see if they're equal to each other. And we'll use that. Let's see, cargo clippy stops complaining. No, still doesn't like that. Comparing trait object pointers compares non-unique vtable addresses. So even doing it this way doesn't help. So here's what I'm going to do then, is I'm going to take the rest of this, I'm going to finish the rest of this chapter, 10.6, and what else? Is there 10.7? There's not. There's challenges, though. And then I'll go back and I'll fix all my tests, because I should have been running the tests all along, right? And I feel very guilty about not having. Zeta says, can I put the Rust error code? I'll put the whole thing in here. Bam! I just spammed chat. Apologies, everyone. But there you go. And what I'll do is, so we'll do 10.6. We'll take a look at the challenges, and then I'll fix the tests. So let's do things that way. Let me get rid of this. Let me switch this back, since it didn't seem to make a difference for Clippy's, from Clippy's point of view. Oh, what's this? Standard pointer is no longer used. And Zeta, what I can do is just push these changes right now. If you want to, if you wanted to play with it directly, get status, get diff. Oh yeah, that's just Clippy. Git add source, git commit, Clippy partial cleanup. All right. So that should be up here. And then if you want to play with it and let me know what you find, that would be awesome. That would be really awesome. Okay, so yeah, let's dive right into local functions and closures and then fix the tests, and then maybe that'll be the whole stream. Our functions are pretty full-featured, but there's one hole to patch. In fact, it's a big enough gap that we'll spend most of the next chapter sealing it up. But we can get started here. Lock's functions implementation of call creates a new environment where it binds the function's parameters. When I show you that code, I glossed over one important point. What is the parent of that environment? Right now it's always globals, top-level global environment. That way, if an identifier isn't defined inside the function body itself, the interpreter can look outside the function in the global scope to find it. Right, we tested that, actually. In the Fibonacci example, that's how the interpreter is able to look up the recursive call to fib inside the function's own body. Fib is a global variable. But recall that in locks, function declarations are allowed anywhere a name can be bound. That includes the top level of lock script, but also inside of blocks or other functions. Lock supports local functions that are defined inside another function or nested inside a block. Consider this classic example. This is a classic example. Okay, so we have a make counter, a function count that increments I and prints I inside here, and we return a pointer to that function. So this I is referring to this I here, but once this scope goes away, right, I think that's what they're saying, is this scope disappears once you return from make counter, so what's counter referring to? So let's actually try it right now. Let's copy this whole thing, shove it right there. And what happens when we run this code? Yeah, undefined variable I at line 4. So it's not finding this I here. Here count uses I, which is declared outside of itself in the containing function makeCounter. MakeCounter returns a reference to the count function, and then its own body finishes executing completely. Meanwhile, the top level code invokes the returned count function right here. I think counter. Oh, this count function, yes. That executes the body of the count function, which assigns to and reads I, even though the function where I was defined has already exited. If you've never encountered a language with nested functions before, this might seem crazy, but users do expect it to work. Alas, if you run it now, you'll get an undefined variable error in the call to counter when the body of count tries to look up I. That's because the environment chain, in effect, looks like this. When we call count through the reference to it stored in the counter, we create a new empty environment for the function body. The parent of that is the global environment. We lost the environment from makeCounter where I is bound. Right. So let's go back in time a bit. Here's what the environment chain looked like right when we declared count. So here's where I is declared inside makeCounter. So at the point where the function is declared, we can see I. But when we return from makeCounter and exit its body, the interpreter discards that environment. Since the interpreter doesn't keep the environment surrounding count around, it's up to the function object itself to hang on to it. This data structure is called a closure because it closes over and holds onto the surrounding variables where the function is declared. Closures have been around since the early Lisp days, and language hackers have come up with all manner of ways to implement them. For JLocks, we'll do the simplest thing that works. In Lock's function, we'll add a field to store the environment. Closure is yet another term coined by Peter J. Landon. I assume before he came along that computer scientists communicated with each other using only primitive grunts and pawing hand gestures. I don't know Peter J. Landon. This is a gap in my education. I am ignorant. He was one of the first to realize that lambda calculus could be used to model a programming language, an insight that is essential to the development of both functional programming and denotational semantics. Okay, I will have to learn about him because he sounds like a very interesting guy. Okay, so we're going to add a closure as an environment within our locks function. What type is it going to take, though? Closure. I mean, it says environment, but we all know that this is really going to be just a reference to an environment. So are we doing an RC? And when we create it, we put the closure there. What else are we doing with the closure? We're going to pass it in there. So maybe this is good enough. Let's find out. Andreal, thank you for the follow. All right. So if we grab the closure here, we're going to pass in an environment ref rc clone closure, which means this is going to say closure rc environment like that. And this, right, we initialize that constructor. When we create a locks function, we capture the current environment. So in visit function statement, let's take a look at that. Here's visit function statement. We're going to set the function to statement and the current environment. So that's going to go here. Self environment borrow. Because right now self environment is a ref cell of an RC, and the reason we have to do this allows for us to do interior mutability, and this outer ref cell allows us to replace environment when we need to. So we have to borrow it whenever we look at it. So I think we just do this, right? And then this, maybe. Let's see if this builds. Nope, of course not. Expected struct RC. Oh. We found ref. Okay, maybe I just take this out. Why is it expecting that? Let's take a look at our locks function again. Yeah, expecting RC environment. Expected reference. Why is this complaining about this? Oh, duh, because, yeah. Okay, so down here, yeah, it's not that simple. This has to be also a ref cell. Because we have to be the same. It has to be the same type. And use standard cell, ref cell. Like that. That can go away then, right? Nope, still not there. Oh, because I messed this up. And this now needs... Is this where we have to put the ampersand here now? And hit F1 by accident. Expected reference. Why is this not I don't want to say borrow because that'll go too far, right? And I can't do that. Oh, maybe this is a situation where I do that. Yeah, okay. And this is not used. Okay, we're not using it yet because we haven't written that part of the code. This is kind of annoying. Is this a situation where I can use deref? I'm gonna try. One of these days I'm going to learn where that gets used. Okay, so that works. That works. I like this a little bit better than that other operator thing. So let's stick with this for now. All right, so we got this working. This is the environment that is active when the function is declared, not when it's called, which is what we want. It represents the lexical scope surrounding the function declaration. Finally, when we call the function, we use that environment as the call's parent instead of going straight to globals. Okay, so that's in lock's function. So instead of going for globals, there's globals, we're going to just use closure. Which might not work. Just like that, we might have to play around with it. No, that worked. This creates an environment chain that goes from the function's body out through the environments where the function is declared, all the way out to the global scope. The runtime environment chain matches the textual nesting of the source code like what we want. The end result, when we call that function, looks like this. All right, so then I is in this make counter, and the closure captures this environment here. And then when this drops the reference to the environment, we still have we're holding on to the reference to it here, so it doesn't go away. Now, as you can see, the interpreter can still find I when it needs to because it's in the middle of the environment chain. Try running that make counter example now. It works. I'll be the judge of that. Cargo run counter. Yeah, look at that. It does work. Functions let us abstract over, reuse, and compose code. Locks is much more powerful than a rudimentary arithmetic calculator it used to be. Alas, in our rush to cram closures in, we have left a tiny bit of dynamic scoping leak into the interpreter. In the next chapter, we will explore deeper into the lexical scope and close that hole. All right, let me push these changes. There aren't too many of them. All right, all we did was add this closure business. So that's in section 10.5? 10.6? Can't remember now. 10.6. Closures. It's very simple to do. All right, so what are the challenges? I don't know if I'm going to do any of them, but let's take a look at them. Our interpreter carefully checks that that the number of arguments passed to a function matches the number of parameters it expects. Since this check is done at runtime on every call, it has a performance cost. Smalltalk implementations don't have that problem. Why not? I don't know. I've never used Smalltalk, so I can't answer that challenge. Locks' function declaration syntax performs two independent operations. It creates a function and also binds it to a name. This improves usability for the common case where you do want to associate a name with a function, but in functional styled code, you often want to create a function to immediately pass it to some other function or return it. In that case, it doesn't need a name. Languages that encourage a functional style usually support anonymous functions or lambdas. Yeah, so this is taking a function pointer that's defined here without a name. And then it binds it to this fn variable. Guy from Mars asked me, hey, are you Robert Nystrom? I am not. I am not that smart. I am just following his book and enjoying it immensely and porting it to Rust. But thank you for the compliment. All right, so then how do you handle the tricky case of an anonymous function expression occurring in an expression statement? So what if you just create an anonymous function without having it bound to a function like that? So I don't know how I would go about doing this. I mean, we can take a really quick look at the parser. We would have to ignore this part of it, right? We'd be able to, we could consume it. I mean, we could consume it if it exists, right? We can do a self check token type identifier. And if it exists, then we can give it a name. Where do we actually put the name here? Right here. Otherwise, we could generate a fake name for it, I guess, if one doesn't exist. I mean, and it would have to be a unique name, right? Because otherwise, if you have more than one in the same scope, you wouldn't want them to overwrite each other. Right? I mean, I think that's the only way to do it. And then here, how would you handle the tricky case of an unfunction expression occurring in an expression statement? I guess that could be done by oh, expression is just an assignment. You could peek here an expression statement and say, is it start with fun? And if so, then make sure there's an identifier after it. Right? But that gets tricky because now you've consumed the... Because you'd have to peek two ahead, right? You'd peek ahead once to see fun. But then you have to get the next one ahead to say, okay, is there a name? Yeah, so I'm not going to do this one either. Is this program valid? In other words, are functions parameters in the same scope as its local variables or in an outer scope? What does locks do? What about other languages you are familiar with? What do you think a language should do? For me, this would shadow this A. And I don't know. I mean, I don't think locks is going to complain if I do this. If I read a cargo run, if I say fun scope A, I'll do a print A, then var A equals local, then print A, right? And then I call scope of foo. Yeah, so the first A is what I passed in, then this guy shadows this one, right? I mean, that's the way I read it, and I think locks is doing just fine there. Okay, we're clean, we're good. Oh, right, I wanted to fix my tests. Let's fix the tests before I move on to the next chapter of resolving and binding. Cargo test, and these all fail because I modified the way the environment works and I didn't bother doing it in a TDD way. I think, are these all in environment? This doesn't satisfy locks result debug. Okay. So they're not all in environment. This one is in interpreter. All right, let's take a look at, let's start with environment. Get these and let's take a look here. Line 98, unwrap. I can't unwrap on the get because we can't call it. I can do okay, right? Let's see. That's line 98. Let's try to run that. No, it still doesn't like it. Expected enum option found enum object. Zeta number says, hey, why do you need pointer equals, by the way? Because I need to implement partial equal for, oh, it's not object. What was it on? Callable. We needed partial equal for callable. For some reason. If I take it out, I think it fails. Somewhere. Yeah. So objects need to be partially equal. Objects need to implement partial equal, therefore if callable needs to implement partial equal. Oops. So it doesn't have to be pointer equal, it just has to be some way of comparing two callables to see if they are equal. So if there's a better way to do it other than pointer equal, then I'm all ears. All right, so this is, maybe this has to be sum, because we change that to an option. Tests. Zeta number says that just seems unsound. It probably is. Like I said, if there's a better way to do it, there has to be, I mean, we could always just return false, always. And just say, you know, functions are never equal to each other, even if they refer to the same data. So all we do is make this a sum, right? Oh, right, I have to change this to okay. What would equality for callable mean? I think for that, it just means, are they pointing to the same function? Or do both RCs refer to the same object, I guess, in memory? Which is why I was going for that, you know, the RC pointer equal thing. All right, so 139. So I think we know how to fix all of these. We just change all these to okays, and we change all these to sums. Right. Do that here for whatever line this is. 151, 153, sum. 561. Oh, that's an interpreter. So did we fix all of the environment ones? Source environment. 139, 150. Oh yeah, okay, so we fixed those. Let's pull up the interpreter. And see what's failing here. 561. Oh right, we have to do the double borrow. So everywhere there's a borrow, everywhere there's terp environment, we have to, oh, is it the only one? Okay, so 575. Borrow. 590. Is this another okay thing? Zeta number says locks func is garbage collected, right? Well, Rust doesn't garbage collect, right? It just waits till the last reference is dropped and then frees the memory directly. So, I mean, it should be cleaned up after we stop referring to it. But like I said, I mean, we could just work around it by just saying return false. Just say they're never equal to each other. Oh, we're almost done. 592. All right, so we got the tests working again. The number says, I mean, partial equal for callable could mean like NaN in floats never equal. Yeah. Yeah, that, I mean, that might be the best solution for this one. Just say false, right? And be done with it. I don't know what that would mean in terms of, I guess we never have to worry about looking them up by hash, right? And we never have, because that would be the key there, is whether or not, if we stick them in a hash map or a hash set, because that'll break that, right? Because if we want to have, look for collisions there, or not collisions, but look them up in a map or a set, or even in a vector. If we had a vector of them, we wouldn't be able to see, are they equal to each other? So yeah, we can just leave it like that. Get status, get add source callable, get commit. Clippy is warning us about pointer equal with RCs. So just punt and return false. Okay, and then the rest of it is test cleanup, cargo test. Oh, yeah. And of course I messed that up. Parker Shamblin says, I just lost to a 7-year-old in chess. I don't know how to respond to that. I'm sorry. Zeta number said, or should it mean if it's the same object on a heap? Yeah. Right? That's what we're trying to go for, is are the two callables pointing to the same heap object? And that's why I was using the RC thing, because the RCs, the reference counters, should be pointing to the same heap object if we do a RC clone on them. Get status, get add source callable, and no edit. Okay, get show head. Yeah, okay, good. So now we can put in, Epic Blog says, does callable include closures? A callable is just, it's a way that I did it in order to avoid having to stick, because I think if I say RC locks callable in here, right, din, then things go sideways in terms of yeah, I don't know how, if we refactored it like this, what that would change. So I wanted to put an actual struct in there that had the function that we could use, or a func that we could use. This, I don't know how that behaves. So it's basically just a wrapper around doing this. That's what the callable is for. Zeta number says, like, the equality defined on closure is really strange from a math perspective. Okay. Yeah, that's a little bit beyond my knowledge base. Okay. Zeta number says it's possible with as star const underscore as star const parens. Really? Is that a syntax that Rust does? Self as const, sorry, star const underscore as star const this, and then other. I don't, does that compile? Oh, other. Okay, it compiles. Does Clippy complain about it? It says, try using this, which we tried. Sure, let's try this. Okay, so now Clippy doesn't complain. Oh no, RCS pointer as const. Okay. Okay. Oh, what did I just do? That was weird. Func, right? And as const. Now we're getting crazy here. I can barely read. Okay, as const this. And do the same thing for other. Yeah, I mean, Clippy doesn't mind this. Okay. All right, and I think we're still at this level here, right? So we can do the editor and vim. Oh, amend. Fix Clippy warning pointer comparison. There. Okay. Oh, something broke. I didn't do it right. Oh, I didn't do an add. Duh. Get add source call. There we go. Yeah. Try it. There we go. Okay. Zaydinmer says, by the way, parentheses means tuple with 0 elements. Oh, the unit. Oh, right. I was reading it as a function called something. But this is as a constant pointer to unit. Got it. Okay. Thank you, Zeta and Epic, for all that help. I think this might be good enough. It avoids Clippy's warnings, and I don't know if we're ever going to need pointer equality, but there it is. And we're in the middle of, oh yeah, fix the tests. Get add source, get commit. Fixed tests. Oh, and now there's an extra new line in there. Oops. Oh no, the new line's gone. Okay. So now we can cargo test, we can cargo run. Print foo. Okay, everything's working. We're good. Nice. Okay, so I have about 45 minutes left, so let's start with resolving and binding. Oh no, our language implementation is taking on water. What? Way back when we added variables and blocks, we had scoping nice and tight. But when we later added closures, a hole opened in our formerly waterproof interpreter. Most real programs are unlikely to slip through this hole. But as language implementers, we take a sacred vow to care about correctness even in the deepest, dampest corners of the semantics. We will spend this entire chapter exploring that leak and then carefully patching it up. In the process, we will gain more rigorous understanding of lexical scoping as used by locks and other languages in the C tradition. We'll also get a chance to learn about semantic analysis, a powerful technique for extracting meaning from the user's source code without having to run it. All right, so a quick refresher for static scope. Locks, like most modern languages, uses lexical scoping. This means you can figure out which declaration a variable name refers to just by reading the text of the program. So the number says, I think pointer equality should be present there because dictionary structured data should use pointer equals to. Okay. Yeah, I will buy that. Okay. So for example, here we know that A being printed is the variable declared in the previous line, not the global one. Running the program can't affect this. The scope rules are part of the static semantics of the language, which is why they're also called static scope. I haven't spelled out these scope rules, but now is the time for precision. This is still nowhere near as precise as real language specification. These docs must be so explicit that even a Martian or an outright malicious programmer would be forced to implement the correct semantics provided that they follow the letter of the spec. That exactitude is important when a language may be implemented by competing companies who want their product to be compatible with others to lock customers onto their platform. For this book, we can thankfully ignore those kind of shady shenanigans. I haven't spelled out the scope rules, but now is the time for precision. A variable usage refers to the preceding declaration with the same name in the innermost scope that encloses the expression where the variable is used. That's a lot to unpack in that. I say variable usage instead of variable expression to cover both variable expressions and assignments. Likewise with expression where the variable is used. Preceding means appearing before in the program text. All right, so this A refers to this A, and this A hides these two A's. Here A is being printed in the outer scope since it appears before the print statement that uses it. In most cases in straight-line code, the declaration preceding in text will also precede usage in time. But that's not always true. As we'll see, functions may defer a chunk of code such that its dynamic temporal execution no longer mirrors the static textual ordering. Right. Yeah, that makes sense. In JavaScript, variables declared using var are implicitly hoisted to the beginning of the block. Any use of that name in the block will refer to that variable even if the use appears before the declaration. When you write this in JavaScript, it behaves like this. Hoist. This I did not know. This means that in some cases you can read a variable before its initializer has run, an annoying source of bugs. The alternate let syntax for declaring variables was added later to address this problem. Okay, since this rule makes no mention of any runtime behavior, it implies that a variable expression always refers to the same declaration through the entire execution of the program. Our interpreter so far mostly implements the rule, but when we added closures, an error snuck in. Before you type this in and run it, decide what you think it should print. All right, so what is this doing? It's calling show A, which is printing A, which should be referring to the global A. And now we have a block, a local A within this block, and we call show A. So now, does this print A refer to this one or to this one? What should it print? I mean, so from my reading of this, I would take it to mean that this A here refers to the global scope A because it's defined. Fun show A is defined before we overwrite it here. But I can see that when we run this show A, this will now be in the local scope. And when we call this function, well, when we call the function, right, we're grabbing the current environment as our closure. So, and this A is now going to be in the current environment, so it's going to grab that one, is my guess. So it should print global and then print block. And is that the right thing to do? I don't know. Scope. I already have scope. I'll call it scope 2 locks. Yeah, it did global first and then did block. Because this one is now in the environment. And now when we call this show A, the closure that we pass into it includes this A, which is going to now print block. I mean, that's fair, right? I mean, that's a fair way to go. As long as you're consistent about it. Okay, if you're familiar with closures in other languages, you'll expect it to print global twice. The first call to show A should definitely print global since we haven't even reached the declaration of inner A yet. And by our rule that a variable expression always resolves to the same variable, that implies the second call to show A should print the same thing. Alas, it prints global block. I know it's totally pathological, contrived program is just weird. No reasonable person would ever write code like this. Alas, more of your life than you'd expect will be spent dealing with bizarro snippets of code like this if you stay in the programming language game for long. Let me stress that this program never reassigns any variable and contains only a single print statement, yet somehow that print statement for a never assigned variable prints two different values at different points in time. We definitely broke something somewhere. All right, in our interpreter, environments are the dynamic manifestation of static scope. The two mostly stay in sync with each other. We create a new environment when we enter a new scope and discard it when we leave the scope. There's one other operation we perform in environments, binding a variable in one. This is where our bug lies. Let's walk through that problematic example and see what the environments look like at each step. First, we declare A in the global scope. That gives us a single environment with a single variable in it. Then we enter the block and execute the declaration of show A. So now we have that closure. We get a new environment for the block. In that, we declare one name, show A, which is bound to the locks function object we create to represent the function. That object has a closure field that captures the environment where the function was declared, so it has a reference back to the environment block, the environment for the block. Right. So now we call show A. The interpreter dynamically creates a new environment for the function body of show A. It's empty space, since that function doesn't declare any variables. The parent of that environment is the function's name. Is the function's closure in the outer block environment. Inside the body of show A, we print the value of A. The interpreter looks up this value by walking the chain. So here, then here, then here. It gets all the way to the global environment before finding it there and printing global. Great. Next, we declare a second A, this time inside the block. And now there's an A here. It's in the same block, the same scope as show A, so it goes to the same environment, which is also the same environment show A's closure refers to. This is where it gets interesting. We call show A again. Now we work our way up, and we see this one. We create a new empty environment for the body. Again, wire it up to that closure and run the body. When the interpreter walks the chain of environments to find A, it discovers a new A in the block environment. Boo. I chose to implement environments in a way I hoped would agree with your informal intuition around scopes. We tend to consider all of the code within a block as being within the same scope. So our interpreter uses a single environment to represent that. Each environment is a mutable hash table. When a new variable is declared, it gets added to the existing environment for the scope. That intuition, like many in life, isn't quite right. A block is not necessarily all the same scope. Consider. At the first marked line, only A is in scope. At the second line, both A and B are. If you define a scope to be a set of declarations, then those are clearly not the same scope. They don't contain the same declarations. It's like each var statement splits the block into two separate scopes. The scope before the variable is declared and the one after, which includes the new variable. Right. So maybe that's why JavaScript did it this way. Right? You create a var here, and so this entire scope contains the var. So no matter where you are in that scope. Whereas the let does the implicit scope splitting. Right? So anything before the let is going to be in one scope, and anything after the let is going to be in another scope. So what are we going to do? Every time we see a var statement, we're going to create a new scope? How are we going to fix this? Some languages make this split explicit. In Scheme and ML, when you declare a local variable using let, you also delineate the subsequent code where the new variable is in scope. There's no implicit rest of the block. Okay. In our implementation, environments do act like the entire block is one scope. Tuesday evening. Thank you for the follow. Closures do not act like that. When a function is declared, it captures a reference to the current environment. The function should capture a frozen snapshot of the environment as it existed at the moment the function was declared. But instead, in the Java code, it has a reference to the actual mutable environment object. When a variable is later declared in scope that the environment corresponds to, the closure sees the new variable, even though the declaration does not precede the function. Yeah. So, I mean, are we just going to create, every time we have a var, we just create a new environment for it? Or no, because it would still refer back to that same one. So that's not the answer either. All right, persistent environments. There's a style of programming that uses what are called persistent data structures. Unlike the squishy data structures you're familiar with in imperative programming, a persistent data structure can never be directly modified. Instead, any modification to an existing structure produces a brand new object that contains all of the original data and the new modification. The original is left unchanged. This sounds like it might waste tons of memory and time copying the structure for each operation. In practice, persistent data structures share most of their data between the different copies. Yeah. And that makes sense as a reasonable optimization there. If we were to apply that technique to environment, then every time you declared a variable, it would return a new environment that contained all of the previously declared variables, along with the one new name. Declaring a variable would do an implicit split, right? So we'd have this, and then the A would go in here, and then we'd walk our way back here and still find the global A. The closure retains a reference to the environment instance in play when the function was declared. Since any later declarations in that block would produce a new environment objects, the closure would see the new variables and our bug would be fixed. Right. This is a legit way to solve the problem, and it's a classic way to implement environments in scheme interpreters. We could do that for locks, but it would mean going back and changing a pile of existing code. All right, let's not change a pile of existing code. I won't drag you through that. Thank you. We'll keep the way we represent environments the same. Instead of making the data more statically structured, we'll bake the static resolution into the access operation itself. What does that mean? We'll bake the static resolution into the access operation itself. Okay. I don't know what he means by this, but maybe that's what we're going to go through, right? So our interpreter resolves a variable, tracks down which declaration it refers to, each and every time the variable expression is evaluated. If that variable is swaddled inside a loop that runs 1,000 times, that variable gets re-resolved 1,000 times. We know static scope means a variable usage always resolves to the same declaration, which can be determined just by looking at the text. Given that, why are we doing it dynamically every time? Right. Doing so doesn't just open a hole that leads to an annoying bug, it's also needlessly slow. A better solution is to resolve each variable use once. Yeah, okay. I get that. Write a chunk of code that inspects a user's program, finds every variable mentioned, and figures out which declaration each refers to. This process is an example of semantic analysis, where a parser tells only if a program is grammatically correct. Semantic analysis goes farther and starts to figure out what pieces of the program actually mean. In this case, our analysis will resolve variable bindings. We'll know not just that an expression is a variable, but which variable it is. Wow, this is long, isn't it? But I'm learning a lot, so this is good. There are a lot of ways we could store the binding between a variable and its declaration. When we get to the C interpreter for locks, we'll have a much more efficient way of storing and accessing local variables, but for JLocks, I want to minimize the collateral damage we inflict on our existing code base. I'd hate to throw out a bunch of mostly fine code. Instead, we'll store the resolution in a way that makes most out of our existing environment class. Recall how the accesses of A are interpreted in the problematic example. In the first correct evaluation, we'll look at the 3 environments in the chain before finding the global declaration of A. Then, when the inner A is later declared in block scope, it shadows the global one, right? The next lookup walks the chain, finds A in the second environment, and stops there. So we go boom. If we could declare a variable lookup always walk the same number of links in the environment chain, that would ensure that it found the same variable in the same scope every time. Let me read that again. If we could ensure a variable lookup always walk the same number of links in the environment chain. So you're saying, so if we're here and we know that we go back 1, back 2, and then find A, the next time we look up A, we're always going to go back 1, back 2, and find it there. To resolve a variable usage, I think that's what he means. To resolve a variable usage, we only need to calculate how many hops away the declared variable will be when in the, how many hops away the declared variable will be in the environment chain. The interesting question is when to do this calculation, or put differently, where in our interpreter's implementation do we stuff the code for it? I mean, we could do it the first time we look it up. Right? We look it up, we count how many times we go back, and then just shove that in here, or return that as part of the variable lookup. And then the second time we say, does it exist, and then just hop back that many times. Since we're calculating a static property based on the structure of the source code, the obvious answer is in the parser. Okay, so that's opposite to what I just said. Aura, hello. How are you? Right, so they're saying do it at parsing time, not during runtime. That's the traditional home and is where we'll put it later in CLOCs. It would work here too, but I want an excuse to show you another technique. Ooh, we'll write our resolver as a separate pass. As a separate pass? A variable resolution pass. After the parser produces the syntax tree, but before the interpreter starts executing it, we'll do a single walk over the tree to resolve all of the variables it contains. Additional passes between parsing and execution are common. Okay, if locks has static types, we could slide a type checker in there. Optimizations are often implemented in separate passes like this too. Basically, any work that doesn't rely on a state that's only available at runtime can be done this way. Our variable resolution pass works like a sort of mini interpreter. It walks a tree, visiting each node, but static analysis is different from a dynamic execution. There are no side effects. When a static analysis visits a print statement, it doesn't actually print anything. Calls to native functions or other operations that reach out to the outside world are stubbed out and have no effect. And there's no control flow. Loops are visited only once. Both branches are visited in if statements. Logic operators are not short-circuited. I'm trying to wrap my brain around this. So basically, we're going to walk the entire syntax tree. We'll do a single walk over the tree, do the variable resolution, and save that somewhere, right? And by variable resolution, that means we're going to record how many hops we have to go back the first time we look at something, and save that somewhere. Variable resolution touches each node once, so its performance is O of n. More sophisticated analyses may have greater complexity, but more carefully designed to be linear or not far from it. It's embarrassing faux pas if your compiler gets exponentially slower as the user program grows. Right, so we try to keep O of n or faster. Fair enough. A resolver class. Like everything in Java, our variable resolution pass is embodied in a class. All right, so I guess we're creating a new struct. Get status. I think we're clean. We are. Let me push these up. Why not? All right, so we're going to have an interpreter. Since the resolver needs to visit every node in the syntax tree, it implements the visitor abstraction we already have in place. Oh! So this is just going to be, yeah, so this is going to be an interpreter, but it has an interpreter in it. Only a few kinds of nodes are interesting when it comes to resolving variables. A block statement introduces new scope. A function declaration introduces new scope. A variable declaration adds a new variable to the current scope, and variable and assignment expressions need to have the variables resolved. The rest of the nodes don't do anything special, but we'll still need to implement visit methods for them that traverse into their subtrees. Zeta number says, very interesting. I agree. This is fascinating part. So when I learned compilers and interpreters way back in the Dark Ages, I didn't learn about any of this. So this is, while the other stuff is mostly refresher, this is really new to me, doing this kind of thing. So even though a plus expression doesn't itself have any variables to resolve, either of its operands might. Right. Because they could be function calls or something. Resolving blocks. We start with blocks since they create local scopes where all the magic happens. All right, let's start with a resolver class. And it looks like we have hash map, list map, and stack. All those come for free. Well, hash map is going to be, we'll have to import that at some point. But list and stack are just going to be vec. And this is going to implement visitor for expert and visitor for statement. Ivan the Raging Python, thank you for the follow. Shrishak says, when I was in uni writing compiler, well, writing compiler means doing shenanigans with parens and brackets using some grammars. Oh. Okay. I did like a Pascal interpreter or something like that. It's been ages since I did anything in this area, so this is good. This is all good for me. Zeta number says, yeah, can confirm. All right. All right, so we have a struct which is going to have an interpreter. So we need use. We're going to need the hash map at some point, but I don't want to import it until we actually need it. Otherwise, Russ is going to yell at us about unused things. So struct resolver is going to have interpreter. We're just going to have an interpreter. And I don't know if I want to make this an RC or not, or if it needs its own interpreter. And then impl resolver pub fun new interpreter. See, this is what I want to say. I think this does need to be an RC. I don't know. Let's find out. So then this just returns a self and self interpreter. Oh, yeah, of course that checks because I didn't actually put it anywhere. Mod resolver. Okay. It still checks. Since the resolver needs to visit every node. Oh yeah, we read that. The rest of the nodes don't do anything special. Okay, so we start with blocks since they create local scopes where all the magic happens. Right, so this is where we now have to get annoyed at the way Rust does stuff, right? Because when you say impl, you know, what was it, statement visitor or something like that? Yeah, impl statement visitor for interpreter. What are these things? These things return void. So we can just do that. And unfortunately now we need to add all of the guys in here. I'm going to cheat here. Grab fn visit. Like this, fn visit. And then we have these guys, and we are going to have to do the expers at some point. And then we'll say impl expert visitor, but I don't know what type it's going to be until we get there. Actually, I want to go back to, I don't want to save that other change. Get back to my interpreter, please. Thank you. Undo. Okay. So these are these. I'm going to comment this out for now. And the only reason I did this, I should have done OK everywhere. All right, so this should still check. Nope. What did I miss? Not found in the scope. Oh, right. We don't have use, create, statement, star. And error. And conflicting, oh, for resolver. There we go. Okay. Tree Shack says, "Are you writing compilers for Java?" I am not writing any compilers on my own. I'm just doing this as a Rust learning stream. Because I want to learn. I want to get better at Rust, and I figured why not stream that. So no, I'm not writing a compiler myself. I'm just learning how to. All right, so we have all of these guys, and it all checks, and now we can add in the code one statement at a time, right? Here's visit block statement is right here. So we're calling something called begin scope, then resolve, and then end scope, and returning null. So I can leave that okay in there. So self begin scope, self resolve, statement, statements, statements, probably like this, right? And then self end scope. So this begins a new scope, traverses the statements inside the block, and then discards the scope. The fun stuff lives in those helper methods. We'll start with the simple one. Okay. So this is where we're going to go down here and say impl resolver and create a function called resolve, which is going to take self and a vec of statements. Let's look up what that type is actually. Block. Yeah, it's just a vec of statements. Okay, so statements is vec statement. Oh, right. And then Rust is going to complain if I do it that way, so or Clippy will. So we do it this way. And what does it return? It returns void, so we don't care about anything. And then so for statement is state, probably not statements like that. Self resolve. Oh, you know what we're doing here? Okay, that's annoying. So it's one thing that Java allows is function overloading, which we can't do in Rust. So we're going to say resolve statement. Right? We have to do it this way, and then I have to write my own resolve. Right? Because here's the resolve statement. Fun resolve statement self. Statement is a statement. If I say statement one more time, statement accept self statement. Oh, let's use the same variable names. Okay, and we're not returning anything. We're just doing stuff. Right, so we're throwing away the result out of this. Right, because except, if we look at this statement except, oh, I don't have it there. Source. Right, if we look at except, it returns a result. So what are we doing with that? We're just ignoring it? I guess. I don't know. Let's find out. So this walks a list of statements and resolves each one. It in turn calls except. And while we're at it, let's add another overload that we'll need later for resolving expression. Okay, so I guess we are going to do the expression one. And this has to be capital E. And I need to pull that in here. Okay. These methods are similar to the evaluate and execute methods in the interpreter. They turn around and apply the visitor pattern to the given syntax tree node. And I'm running out of time. I have less than 15 minutes left, so I don't think we're going to get... There's a lot here, right? we can get started with it, right? And then I'll just have to stop when I run out of time. All right. Begin scope. So we have scopes.push, and scope is this thing here. The real interesting behavior is around scopes. A new block scope is created like so. So we have, I'm going to add scopes here, and it's a new stack. Oh no, it's a map. It's a vec of hash maps of string boolean. Okay, so this is where we add the use standard collection hash map. So this is going to be a vec of hash map of string to bool. Oh, and we're going to have to modify it. And because of the way I defined this without a mutable self in it, that means we're going to have to ref cell this guy so we can mutate it. Right? And that means this here needs to create it. Oh, not interpreter colon, scopes colon. And this is going to be a ref cell, new, vec new. Right? And then in begin scope, script sh. Thank you for the follow. All right, so we need to write begin scope. So that's going to look like this: fn begin scope self. Oh, it doesn't take anything. It just pushes a new. So we say self scopes borrow. Come on, Luxab. Thank you for the follow. Hello. So borrow mu dot insert. Oh no, append, right? This is a vec, so we're gonna, yeah, push works. And then we'll just say a new hash map. Is that it? That's all we have to do? Is that gonna check? Of course not. Oh, collections. End scope doesn't exist. Except self doesn't work. The trait, oh, okay, yeah, we don't need this yet. Because we don't have that trait implemented. So okay, we can ignore that. Yeah, so end scope doesn't work. I'm going to comment this guy out because we're not using it yet. And so now we'll add end scope, right? Yes. All right, so lexical scopes nest in both the interpreter and the resolver. They behave like a stack, right? So that's why we're just doing the push. The interpreter implements that stack using a linked list, the chain of environment objects. In the resolver, we use an actual Java stack. Okay, and we're using a vec in Rust, so that's fine. This field keeps track of this stack of scopes currently in scope. Sure. Each element in the stack is a map representing a single block scope. Keys, as in environment, are variable names. Right. So just like in environment, right, are variable names. The values are booleans for a reason I'll explain soon. I'll explain later. Okay, the scope stack is only used for local block scopes. Variables declared at the top level in the global scope are not tracked by the resolver since they are more dynamic than locks. When resolving a variable, if we can't find it in the stack of local scopes, we assume it must be global. Okay. Since scopes are stored in an explicit stack, exiting one is straightforward, so we will pop. And scope self scopes mut pop. Done. That was easy. Now we can push and pop a stack of empty scopes. Let's put some things in them. How long is this section? Because, okay, maybe we can do, yeah, 3.2, and then we'll call it a stream. Does this check? It does. We have 12 warnings because we're not using anything in here. Oh yeah, see, this has a result that must be used. There must be try-catch stuff that we have to handle. I wonder if we can do, just say result, this, locks result, and let the level up from that handle it. We still have 12 warnings, so it didn't fix anything. Oh, now we have that one, yeah. So 74. So this just can get a question mark. And now we have an error because this guy doesn't return result. This locks result. Expected results, and now this has to be okay. There, we still have 12 warnings. Wow. I'm not fixing anything here. 42. Now it needs to have that. Okay. Do we get down to 11? Finally. All right, and what are those issues? Oh yeah, we're not using any of those guys. Okay, I can live with those because we'll get to those eventually, and we're never creating one. So that's, well, I'm sure we're going to create one at some point. Interpreter is never used. All right, so resolving variable declarations, we have visit var statement, which is right here. Oh, now we have this declare and define. Okay, self-declare, statement name. And I'm going to assume that also is going to do that. If statement initializer, if let sum in it is equal to statement initializer, then we're going to resolve, self-resolve, statement, in it, like that, question mark, right? And then self-define, probably this, statement name, as I'm guessing, right? And then we can do that. So we do a declare and then resolve all the statements within the var and then do a define. And we're going to have to figure out what the difference is between declare and define. We split binding into 2 steps, declaring and then defining, in order to handle the funny edge cases like this. What happens when the initializer for local variable refers to a variable with the same name as the variable being declared? We have a few options. Haita, I'm not an anime character, but thank you for the compliment. So a few options. Run the initializer and then put the new variable in scope. Here the new local A would be initialized with outer variable, the value of the global one. In other words, the previous declaration would desugar to this. Right, that makes sense. Put the new variable in scope and then run the initializer. This means you could observe a variable before it's initialized. So we would need to figure out what value it would have then, probably nil. That means a new local A would be reinitialized to its own implicitly initialized value, nil. Now desugaring would look like this. Make an error to reference a variable in its initializer. So have the interpreter fail either at compile time or runtime if the initializer mentions the variable being initialized. Do either of those first 2 options look like something a user actually wants? Shadowing is rare and often an error, so initializing a shadowing variable based on the value of the shadowed one seems unlikely to be deliberate. The second option is even less useful. The new variable will always have the value nil. There's never any point in mentioning it by name. You could use an explicit nil instead. Since the first 2 options are likely to mask user errors, we'll take the third. Further, we'll make it a compile error instead of a runtime one. That way, the user is alerted to the problem before any code is run. In order to do that, as we visit expressions, we need to know if we're inside the initializer for some variable. We'll do that by splitting binding into 2 steps. So the first is declaring, right? So we did the declare here. So now we're going to have this in here. Declare self, and we're going to take a name as a token. I'm going to do a token ref. And do we need, maybe we don't need to do, I put question marks here anticipating we would need error returns, but maybe we don't. Resolve statement does. So I'll leave that there. Okay. So declare is just, we'll have a void. I'm not going to worry about. Return results. So if scopes is empty, return. If it's not empty, then we're going to peek and then put in that peaked value, in that peak scope, this value. I don't think we can break it up like this because of the ref cell. I think we have to do it all in one step because of the ref cell. So I think we have to say self scopes borrow mute last to get the last one out of the vector, and that gives us an option that we have to unwrap, right? And then in there we can say insert name, I think we use name as string, false. Will that work? Token is not found. Okay. I'm going to move this down here just for now. And I forgot a semicolon. Oh. Oh, so this is a resolve expr. Initializer is an expr. Oh, so this is expr, which means this has to be an expr, which means we now have to pull this in. Oops. And I'm going to change all these objects into these guys and change this to just return OK. Okay, now we have this. And now we can pull this in. Right? And now we check. Oh, for resolver. Doesn't like it because I didn't do this. There we go. Okay, so now resolve expr. The question mark can't be applied to. Oh, right. So I need to do this. And this is going to be result. Box result. I don't know if this is supposed to be a unit or if it's supposed to be object. I don't think it's supposed to be object. That wouldn't make sense, would it? And then define doesn't exist. Okay, so we're going to do define next, I assume. The declaration adds the variable to the innermost scope so that it shadows any outer one and so that we know the variable exists. We mark it as not ready yet. I guess that's what the false means, by binding its name to false in the scope map. The value associated with the key in the scope map represents whether or not we have finished resolving that variable's initializer. After declaring the variable, we resolve its initializer expression in that same scope where the new variable now exists but is unavailable. Once the initializer expression is done, the variable is ready for primetime. We do that by defining it. So this just does the same thing except changes it to true. Would it be an error to, I guess not, because if scopes is empty, we're in global scope, right? But it would be an error if it doesn't exist here. I'm just trying to think of, should we use the entry? So if self scopes borrow is empty, then we're going to say self scopes borrow mut last unwrap insert name as string true. We're just going to not care. We'll just blast that in there. Right? Okay, so this is this. Does this check? It doesn't check. Oh, right. And this was bothering me before with the callable interface, right? No? I had to do an into somewhere. Yeah, here, in the locks function. And why did I have to do that? And I think that's the problem we're having here, because it's the same issue. We're trying to return a string, and that string should just return a string. Why does it return an ampersand string? Clone? I don't know. That's why it returned an ampersand string. Okay. And then in our locks function, we can switch that back to, we don't need the into anymore. Okay. Okay, so that's that issue. Okay, we're close. Cannot borrow is mutable. Really? Why not? We're in a borrow mute. Do I have to do this now? No, that still doesn't work. All right, so I have an issue here where I can't actually insert anything into my resolver, even though I did a scopes borrow mute, got the last entry in the vector, unwrapped that, and then tried to do an insert on the hash map. So, oh, and I am way over my time, so I'm gonna have to stop here. I've gone too far. I've gone too long, and then we'll figure this out tomorrow. So unfortunately, we're stuck in the middle of this resolve. We're about halfway through the resolver chapter, so we'll resolve the resolver chapter tomorrow. All right, so I'm gonna leave it there. Git status. Yeah, the last thing I pushed was just before. Yeah, we fix our test, we fix our clipping warnings, and we finished the closures from the last chapter. So we will leave it there. All right, thanks everyone for hanging out with me. Thank you Zeta Numbers and Epic, especially for the help with the pointer stuff in the callable. And I will hopefully see everyone tomorrow, where we'll finish up resolution and get this all working and fix that bug that was pointed out about looking up the wrong variable. All right, and with that, I will see you later. Take care.